Hello everyone, this is lesson 19, derivative involving exponentials based on E at this lesson. So how do we do derivative of e to the x power, right? Then e to the x power is a very nice function. We get the same, but then all the time we have to use a channel, right? So we have e to the u, then we want to derivative respect to u, right? That means looking at the derivative, looking at the derivative, we're looking at the u derivative with respect to x, yeah? So let us do this one. Also, we have a general version. Y equal to e to the expression, then we want to derivative, then expression prime, then we have e to the expression, same as e to the x power, but then we have to make a channel, right? Okay, let us do this. Y prime, we do derivative of x squared, it's 2x, yeah? Now, we keep the coefficient. What's the derivative of e to the x power? It's e to the x, yeah? Keep the coefficient free, e to the x. It's the same, right? Okay, for the second term. All right. This one, we want to derivative the first term. Keep the coefficient, then we get the same. Then we knew the natural log of x. We want to derivative, then we have a 1 over x, yeah? Okay. Now, we want to derivative. Okay, how do we do this one? We can we can simply derivative like this by using product rule. We can distribute. Then we have 500 minus 500 e to the negative 0.1x, right? Okay, now we want to derivative of first term, then we get 0. Second term, we keep the coefficient and drop the power. And then we have e to the negative 0.1x, yeah? We keep the same. Okay, let me explain better way. E to the x, derivative, then we get e to the x, yeah? So we have e to the u, then we have e to the u times u prime, right? Okay, so we have, this is a e to the u, right? Then u is this one, right? So this is a u prime. Make sense to you? Okay, I think I did it really quick, this one. Okay, let's do this one. So it's a positive. It's a positive. And then 500 times 0.1, which is 50. We have e to the negative 0.1x. So let you put, it's better. Yeah. Okay. So if you want, you can try the product rule, but there's more work, right? Okay, let's do next one. Okay, so we have, once again, e to the u power prime, then we have e to the u times u prime. So in that case, u equal to x squared minus 1, right? All right, then let's derivative e to the x squared minus 1. Let me do slow at this time. Derivative respect to x squared minus 1. That is u prime, right? Okay, then we have e to the x squared minus 1. And derivative of x squared, which is 2x. So we can rewrite the 2x e to the x squared minus 1. Okay? All right. This one, we must use a product rule at this time because there's nothing. The alternative method, we can use that. So this is u, v, then we want to make s prime over t, then u prime v plus u v prime product rule, right? Okay, then that will be s prime over t derivative respect to t squared v plus u v prime e to the t prime. Okay, we want the derivative with respect to t squared, which is 2t. We have e to the t plus t squared. We want the derivative with respect to t, which is e to the t, right? We can just leave. All right, next one. So we want the derivative with respect to x. The first one has x, right? And then this is a power. So we drop the power, reduce by 1. Then second term, we want the derivative of this. Then same thing, right? Okay, then minus e to the x power. That's it. All right, be careful x, yeah? When x, if we have x to the n, then drop the power and minus 1, yeah? All right. Next one, we have, I can make it smaller, okay, smaller. With the US Department of Health and Human Service data from 2002 and projected to 2024, the total public expenditure for health care age can be modeled by h equal to that, where t is the number of years past 2000 and h is billions of dollars. If this model is accurate, at what rate in billions of dollars per year will the change in 2020? Round one decimal places. Okay, so we have the function. They said at what rate, right? That means we want to find the derivative, right? Derivative, which is h prime. Okay, so h prime over t in that case Okay, keep the coefficient 1500. Now we have e to the u prime, then e to the u times u prime by chain rule, right? Okay, now we keep the same thing. And we want to make the chain rule 0.053t. Okay, then we have 1500 e to the 0.053t and derivative of 0.053t, which is the coefficient, right? So which is 0.053. Okay, if we calculate, we have 79.5 e to the 0.053t. Now we have billions of dollars per year. So billions. Of this is correct, billions, yeah. Dollars per year. Okay, now we want to know when t equal to 2022. So when t equal to 2022, so since they said the past to 2000, so 2022 minus 2000, so we can say the 22 there. So h prime of 22. So we have a 79.5 e to the 0.053 and t equal to 22. So we have $255.1 billion per year. Okay. All right. So we have one more questions here. So after the end, advertising campaign, the sales of a product is given by that, where S is weekly sales in dollars, and T is the number of weeks. Find rate of change. We knew how to find, right? They already give us the S over the T means S prime over T. Okay, now, first one. Let me copy this one. S. So we have S prime over T. So once again, e to the U derivative e to the U times chain rule U prime over T. In that case, just U prime, right? All right, so we keep the coefficient 700,000 e to the negative 0.5t. And we want to derivative with respect to t. Okay, then we have 700,000 e to the negative 0.5t, and we have a negative 0.5. If we calculate, we get this is a negative $350,000 e to the negative 0.5t. Okay, now they ask us this one. From looking at the function, explain how you know cells are decreasing. Okay, the function is exponential decay model because we get what? Negative, right? So it's decay. And additionally, the derivative of a given function is always negative. There you go, right? So this is a decay. And this is negative, right? Okay, so this is from lesson 9 we had before. Let me move this one here. Oops. So we learned that we have a C times, which is the initial for C, and then we have a base. Then we have a negative exponent. Then this is a decay, right? If we have positive exponent, that's a growth, right? So this is a decay. So let me write down. Negative. Telling us. Yes. Okay. All right. Thank you for watching. Bye.